Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 6.1, the Standard Normal Distribution. In this lecture, we're going to introduce the Standard Normal Distribution by first taking a look at density curves, and then we'll get into what's called the Uniform Distribution as an introduction to the Standard Normal Distribution, and then we'll get into the Standard Normal Distribution itself, talk about some of its properties, how to use Zscore Tables, how to find percentiles, and finish with a discussion on critical values. So, as you probably already guessed, this lecture is about the Standard Normal Distribution. Standard Normal Distributions have three specific properties. One is that the graph is bell-shaped. Two, the mean of the distribution is equal to 0, and 3, the standard deviation is equal to 1. If you have these requirements met, then you have a standard normal distribution. It's also important to note that the area underneath the curve represents the probability associated with the bounds of that area. We'll get into that in more detail in the lecture. We'll also get into the fact that the bounds of that area correspond to z-scores. So, in essence, we have z-scores that lead us to the bounds of the area under the curve, which lead us to the area under the curve, which lead us to a probability. And we can actually go through that process in reverse. We can start with a probability, which gives us a certain area under the curve. That area in the curve has a bound to it, and those boundaries are z-scores. First, let's talk about the density curve. So, a density curve is simply the graph of a continuous probability distribution. It doesn't necessarily need to be bell-shaped like the standard normal distribution. It can have pretty much any shape that a given distribution has. So the density curve is simply what we call the line that we use to graph out the probability distribution. But in order to be a density curve, it has to satisfy two very special properties. The first is that the total area underneath the curve must equal 1. And the second is that every point in the curve has a vertical height that is 0 or greater. In other words, you're never going to see the density curve fall below that horizontal x-axis. Now, it's this property of the density curve that the total area has to equal to 1, which allows us to associate areas underneath the curve with probabilities. Because as you remember, one of the properties of a probability is that it is a number from 0 to 1 inclusive. So by specifying that a density curve has to have a total area underneath the curve of 1, then that allows us to assign areas underneath the curve to be probabilities of interest. To help us understand this concept of the area under the curve as a probability, we're going to talk about the uniform distribution before we get into the standard normal distribution. And the reason is that the uniform distribution has a really set shape that we can easily understand, especially when we're looking at areas. So uniform distribution is simply a set of continuous random variables that are spread evenly over a range of probabilities. So when you graph it out, it looks like a box. And so the graph you see here is a uniform distribution. It is shaped like a rectangle. Now, something to note is that uniform distribution can have a number of different heights to it. So it has a range of values along the x-axis from A, which is the minimum value, to B, which is the maximum value. And sometimes the height of the uniform distribution is given, and sometimes it's not. And when it's not, you're always going to use this formula here to calculate the height of your distribution, the reciprocal of the difference between your maximum values, or in essence, the reciprocal of the range. Let's use the area underneath the curve for a uniform distribution to find probability. Suppose we have a data set for the voltage in a simple direct current circuit connected to a 1/2 volt power supply. So we're going to close the circuit 1 second after we start the clock. And when we close the circuit, that lets current flow through the circuit. So therefore we have a potential difference, which is the voltage. And the voltage across the circuit is constant because it's a DC circuit. So it's going to be equal to that of the power supply for as long as we leave the circuit on. So 1 second after we start the clock, we throw the switch, power flows through the circuit, we get a voltage readout, and then 2 seconds later, we're going to open the circuit, so now there's no more current flowing, and we therefore do not have a potential difference. So we get a graph that looks like what you see here on the right side of the screen. This is a uniform distribution, because while the circuit is on, the value associated with each random variable within the range of values while we have the circuit on, it's going to be the same. So therefore, we could say that those random variables are uniformly distributed across that range. What then is the probability that a randomly selected time will be greater than 2.5 seconds? We can solve this problem graphically looking at the graph that we have here on the screen. Or we can basically draw our own graph that we can mark up, and we can use that to illustrate how the different parts fit together to find the probability. What we're looking for is this area underneath the curve here, shaded in green. So we want starting at 2.5 and everything that's greater than 2.5. So this slice of the rectangle here represents the area under the curve that's to the right of x equals 2.5. So we get that shaded area under the curve. Now notice that it's a rectangle. We can easily find the area for a rectangle. It's length times width. So we can calculate the length and the width. The length is simply the height of the rectangle on the graph, which is 0.5. That's equal to the voltage here that you see displayed. And then this distance here is the width, and we can get that by subtracting 3 from 2.5 to get that value there, which is going to be 1/2. So if we multiply those together, we get 1/4 or 0.25. So the probability that a randomly selected time will be greater than 2.5 seconds is 25%. Let's take a look at some more uniform distribution problems, making some notes along the way. So typically what you find with the uniform distribution problem is that you're asked to find a probability. And the expectation when you're asked that question is that you're going to calculate the area under the curve to find it. Now, oftentimes you'll see that the height is given with a problem, but sometimes the height is not given. And as I mentioned before, in that case, you must assume that the height is a function of the range of the distribution. In essence, you're taking the reciprocal of the range. I find an easy way to solve these types of problems is to draw a picture. So the first step I do is I just draw a simple rectangle. And then the next step is to label the range of the distribution with the max and min values on a horizontal axis. Next, I calculate the height, which, if it's not given to you in the problem, is going to be the reciprocal of the difference between the max and the min values that you use to label the range at the bottom of your rectangle. Finally, we look for, calculate the area of interest. So if we were asked to find a value with the x random variable being half the range, then we would mark that at half the range. And then if we're asked to find something greater than that, then we calculate this area here that you see shaded in red. So what we're looking at here in this instance is the probability that x is greater than half the range. Let's look at a specific problem to illustrate how these steps work. So the time a customer must wait in the checkout line of a given retail store is uniformly distributed between 0 and 7 minutes. Now, find the probability that a customer must wait more than 5 minutes to check out. So we're going to go through the steps that we just went through to solve this problem. So the first step is draw a rectangle. Okay, here's our rectangle. here at the bottom of the screen. Next, we're going to label the range of our distribution. Well, the range comes from the problem statement itself. If you look in the problem statement, it says that the wait times are uniformly distributed between 0 and 7 minutes. This then is the range that we will apply to our rectangle. So we put those numbers here on the bottom of our rectangle. So 0 is the minimum value and 7 is the maximum value. The next step is to calculate the height. Notice in the problem statement it doesn't say anything that will give us an indication of what the height would be. And so that means that we have to take the reciprocal of the range in order to calculate the height. So to do that, we're going to take the max value of 7, subtract the min value of 0, and then take the reciprocal. And that gives us a height of 1/7. So now we've got the range, we've got the height, so now we need to figure out which area inside the rectangle is the one that we need to calculate. So we identify that area and then go ahead and calculate the area. Where are we going to put our random variable? Well, if you look at the problem statement, it says find the probability that a customer must wait more than 5 minutes. So we're going to start the area of interest at 5 minutes and then look at the area above that. So we're looking for the area between 7 and 5 underneath the rectangle. We can calculate that area, and that will be the probability that our random variable x is greater than or equal to 5. So the area is simply length times width. We've got the length, so to speak, from the height of the rectangle, if you will. That's going to be the 1/7. And then 7 minus 5 gives us the width. So when we multiply all that together, we get 2/7, which is 0.286, or 28.6%. This is the probability that a customer is going to wait in line more than 5 minutes to check out. Let's look at another problem. Suppose that the amount of gasoline a particular service station sells each day is uniformly distributed between 2,000 and 5,000 gallons per day. Find the probability that the station will sell between 3,500 and 4,000 gallons today. So, this is a uniform distribution problem, so the first step is going to be what? Like we said, draw a rectangle. That's our first step. So go ahead and draw a rectangle. And now that we're drawing a rectangle, the next step is to I hope you said label the range of your distribution. So what's the range of this distribution going to be? I hope you said between 2,000 and 5,000. That's going to be the range for our distribution. So we're going to label our rectangle. 2,000 is the minimum value and 5,000 is the maximum value. What's the next step to solving the problem? It's going to be calculating the height of the rectangle. So with that, we're going to calculate the height. There wasn't anything given in the problem statement to indicate what that height would be. So that means we have to take the reciprocal of the range. So we're going to take 5,000, subtract 2,000, and then take the reciprocal. And when we do that, we get 1/3,000. This is the height of our uniform distribution. The final step, identify and calculate the area corresponding to the probability of interest. What's the probability of interest here? Yes, we want to calculate the probability between 3,500 and 4,000 gallons. So that's going to be the markers for our area. So we label that there on our rectangle and shade in the area of interest. Now that we know what area we're looking at, we can now calculate that area by taking length times width. So the area will then be our probability. The length is just going to be the height that we calculated earlier, 1/3,000. The width is going to be the difference between 4,000 and 3,500. If we take those values and multiply them together, that gives us the area that we're looking for. When we do that, we get 5,000 over 3,000, which reduces to 1 over 6, which, when we punch out on our calculator, is 0.167. So there's a roughly 16% probability that the station will sell between 3,500 and 4,000 gallons of gasoline today. Now we can understand a little bit more about this idea of the area under the curve being the probability that we're interested in calculating. Let's go ahead and look at the standard normal distribution and some properties that it has. So I mentioned earlier, standard normal distributions have a mean value of 0 and a standard deviation of 1. Because standard normal distributions are formed with a density curve, the total area underneath the curve is equal to 1. Now recall from our previous work that z-score is simply the distance a given random variable is from the mean value. And so calculating a z-score will allow us to standardize any normal distribution. So we can have data that's normally distributed, and it might have a mean that's not 0 and a standard deviation that's not 1. Very often you'll find that's the case. But if we standardize the normal distribution, then that opens up a special set of tools in a section of our toolbox that we can use with the standard normal distribution. And this is the reason why we want to standardize the normal distribution, so that we then have access to those tools. So, a little quiz on what we just talked about. Identify whether the normal distribution presented is the standard normal distribution. So here we have a distribution with a mean of 0 and a standard deviation of 1. Does this normal distribution qualify as a standard normal distribution? Well, I hope you said yes, because this is the standard normal distribution, a mean value of 0 and a standard deviation of 1. How about this example? We have a normal distribution with a mean value of 1,010 and a standard deviation of 20. Would this normal distribution qualify as a standard normal distribution? I hope you said no, because no, this is not the standard normal distribution. Remember that the definition of a standard normal distribution is a normal distribution with a mean value of 0 and a standard deviation of 1. If you don't have those pieces in place, you do not have a standard normal distribution. Let's talk for a moment about z-score tables. So we were calculating earlier the area under the curve for the uniform distribution, which is easily done since the area under the curve for a uniform distribution is a rectangle. So all we have to do is find the length times the width. Well, it's a little bit more complicated to find the area underneath the curve when it's not a standard shape like a rectangle. So if you look at that bell-shaped curve that we have for the normal distribution, you might be wondering, gee, how do we find the area underneath that curve? And that's where the power of integral calculus comes into play. Now, in the old days, and I say old days because I'm talking about the old school days where we were solving statistical problems before we had, widespread use of software that was calculating everything for us. We didn't want to have to perform integral calculus underneath the density curve for a normal distribution every time we wanted to find a probability. So that gave birth to a table of z-scores. What has been done is, for every possible z-score that we could have for a standard normal distribution, we have actually already done the integral calculus to find the area underneath that curve up to that z-score. And that's what's given birth to the z-score tables. What you see on the screen here is a portion of a z-score table. Z-score tables typically exist in two parts. One with z-score values that are negative, so these are values that reside to the left of the mean value, and then what you see here is a portion of the positive half of the z-score table, which is values of z to the right of the mean. The areas that are calculated in a z-score table are typically those to the left of the z-score. So if you want something to the right of the z-score, you end up having to take the complement of the number that you find in the table. We'll go through all of that here momentarily. The thing you need to understand up front about the z-score table is that these z-scores that we were calculating earlier correspond with horizontal values of random variables that we would place on the horizontal axis. And these serve as the boundaries for the area underneath the curve, the area being the probability that we're interested in finding. Let's illustrate how to use a z-score table. It's really not that complicated, but it's not something that's generally intuitive to the average person. As I said before, the values that you see in the table represent areas to the left of our z-score of interest. The z-scores, however, are listed in two parts. One part is listed along the left side in a column, and the other part is listed along the top in a row. Let me illustrate how these two parts come together to give us our z-score. We're going to do this by finding the area to the left of z equals 0.64. First, we recognize that 0.64 is the sum of two other numbers, that being 0.6 and 0.04. So we can add these two numbers together to give us the z value that we're interested in. Now we're going to identify the row associated with the first number, 0.6. So we look at our z-table and we find the row that corresponds with z equals 0.6. And that's this row right here. Next, what we're going to do is identify the column that's associated with the other number that we added together to give us 0.64. That's the 0.04. So we look for the column that's labeled with the 0.04, and we find that column right here. So now we have a row of interest and a column of interest, so the intersection of those two is going to be our area of interest. This gives us the area underneath the curve to the left of z equals 0.64. That area is 0.7389. This is the same as the probability that z will be less than or equal to 0.64. So this area represents a probability that we're randomly selecting a z-score that's less than 0.64. Notice the z-score forms the boundary of that area underneath the curve, and that the area underneath the curve is a probability. Now, we can also run the same procedure in reverse to convert probabilities into z-scores. So if we're given a probability and we want to identify a z-score, we can easily do that by running this process in reverse. Look for the area in the values underneath the table, and then back calculate with the column and row headings to give us our z-score. There's some considerations we need to make when using z-score tables. The first is that the z-score tables are to be used only for the standard normal distribution. So if you have a normal distribution that's not standard, do not use the z-score tables until you've standardized that normal distribution. As I mentioned before, the table usually takes up 2 pages. One half is for negative z-scores and the other for positive z-scores. Each value in the table body is a cumulative area from the left up to the boundary specified by the given z-score. Now, once in a while, you'll find someone who's published a z-score table where it's listing areas to the right. You can always tell what you're dealing with if you, typically towards the top of the table, you'll see a graphical depiction of an area underneath a normal distribution curve. And the shaded area tells you if you're looking to something to the left, which is what you see 9 times out of 10, or once in a while, you'll see the area shaded off to the right. And that graphic there at the top of your chart tells you what area you're looking at when you're looking at the numbers inside the Z-score table. Now, when you're working with a graph, please do not confuse z-scores with areas. Z-scores are horizontal values that appear on the horizontal axis. Areas are underneath the curve, and they correspond with probabilities. So the z-score is going to correlate with the number of standard deviations a random variable is from the mean. It's a distance along the horizontal scale. The area, however, is the region underneath the density curve, and it's associated with the probability. So please do not confuse the z-score with the area. They're two very different animals. Finally, the part of the z-score denoting hundredths is found across the top. So the z-score is actually separated out into two parts. One part appears along the side. That's everything but the hundredths part. And then the hundredths part is listed up across the top of the table. Let's look at an example where this is actually used in the real world. So you can take a bone mineral density test to help identify the presence of osteoporosis. The results of this test are commonly reported as z-scores. So we're asked to find the probability that the bone density test reading for a randomly selected adult is less than 0.46. So we go to our z-score table. Since the results of the test are commonly reported as z-scores, you can take that as sufficient evidence, if you will, that we're using a standard normal standard normal distribution, and therefore we can use our z-score table. The first step is to recognize that the z-score is in two parts. So if we want to look at something less than 0.46, we have to take the 0.46 and separate it into 0.4 and 0.06. Then we find the row for 0.4 and the column for 0.06. We can do that here by looking at the partial z-score table that we have on the screen. And here we have the row for 0.4 and the column for 0.6. The intersection of those two will be our probability. So here the intersection lands on 0.6772. This then is the probability that a bone density test reading for a randomly selected adult is less than 0.46. Now, what is the probability that the same reading is more than 0.46? Well, to do that, we can actually use the complement to calculate it. So we take 1 minus the probability that our z-score will be less than 0.46, and that gives us the probability that our z-score will be more than 0.46. Now, some of you may be wondering, why are we using the 1 minus? Why are we using the complement? Remember that the area that under the curve it's given in your z-score table is to the left. But if we want to calculate the probability of more than, then we need the area to the right. So in order to get the area to the right, we simply take the total area under the curve, which is 1, subtract out the area to the left, and that leaves us the area to the right, which in this case is 0.3228. Z-score tables are really handy for finding percentiles. Suppose we want to find the 95th percentile for a data set of bone density test results conducted at an area hospital. Well, just use the Z-score table to find the 95th percentile. We can actually use this method to calculate any percentile. So let's go through and I'll show you how easy this is to use the table. Look for 0.9500 in the area values that you see there in the table. So go through and look and see if you can find 0.95. I'll give you a minute to see if you can find out where it would be. Hope you're looking at this part of the table right here. 0.95 does not exist itself in the table. It resides between two values that are listed in the table, 0.9495 and 0.9505. And in fact, if you look at 0.95, it's exactly in the middle between those two values that are listed in the table. So what this means is we're going to have to do some interpolation. Now, if you saw the interpolation example I was giving in class a little while ago, don't fret too much. This is pretty much the only value that we're actually going to need to interpolate. And that's because this 95% value comes up pretty often. So what we do is we reconstruct the z-scores from the row and column headings. Because 95% is directly in the middle between the two values that are listed, but they're in the same row. So I know that my z-score is going to start with 1.6 because that here is the heading for the row in which these two values are found. The other part of the z-score, however, is going to be smack dab in the middle between the 0.4 and the 0.04 and the 0.05. So if we had a column heading that was exactly in the middle, then the 0.95 would be listed. So what we're really looking for our column heading is 0.045, directly in the middle between 0.04 and 0.05, just like 0.95 is directly in the middle between the two values that are listed in the table, 0.9495, 0.9505. As I mentioned before, the row heading is 1.6, so now we have what we need to reconstruct our z-score. We're just going to add those two numbers together, and that gives us a percentile, the 95th percentile, 1.645. Typically, when you're working these percentile problems for your homework assignments, you can just take the number that's straight off the table, and you're not going to be looking for a number that you have to interpolate. You just find a number that's straight off the table. We have what's called two-tailed areas. So sometimes we're looking for not just an area that's on one side of the curve or the other side, but we're looking for an area in both of the tails of the distribution. So some of the area of interest is in the tail on the left, and the other part of the area of interest is in the tail on the right. Typically, when you have a two-tailed area, the area underneath each part is going to be the same. So you've got the total area underneath the curve of interest divided in half between the two tails. So one half goes on the left, one half goes on the right. Here we have the same bone density data set that we had previously, and we're asked to find the z-scores that separate the bottom 2.5% and the top 2.5%. Remember, the z-scores are the boundaries for our areas under the curve. So the boundary for the bottom 2.5% and the boundary for the top 2.5%. So that means that the area underneath each of those shaded portions is 2.5%, or 0.025. So to find the top 2.5% z-score, we'll just start with that one. Let's look for 0.975 in our z-score table. Why are we looking for 0.975? Well, because the total area under the curve is 1, and so if we subtract 2.5 from 1, that's going to give us 97.5%, and that's what we want. The area to the left of the z-score is what's reported in the table. So we want to find this area to the left of this z-score here. And we do that by taking the complement of the 2.5%. So now let's look in the table to see, can we find where is 0.9750 in our z-score table? Hope you find it right here towards the bottom. So now we have our value of interest. So now we go and we get the headings for our row and column. So we've got 1.9 for the row and 0.06 for the column. If we add those together, we reconstruct our z-score, and that gives us the 1.96. Now, we can do the same thing with the bottom 2.5%. The area that we want is to the left of the z-score. So all we have to do is get the second half of the z-score table that's showing the negative values, find 2.5% there in the area section, and then reconstitute our z-score from that. That's one way to approach this problem. The other way to approach this problem is to recognize that the standard normal distribution is symmetrical about the mean. So we've got the same area under the curve, so that means the z-score for the top portion is going to be just as far away from the mean as the z-score from the bottom portion, because the two halves are mirror images of each other. So all we have to do is just take our first z-score and change the sign. So we get negative 1.96. Now, if you want to verify this, go ahead, get the second half of the z-score table that's listing the negative values, look up 0.025 and reconstruct your z-score. You will see that you get negative 1.96 from that exercise. I think, though, more often than not, when you're working your problems, you're going to be using the tables less, and you're going to be using software like StatCrunch a whole lot more. StatCrunch has a number of different calculators, as you've seen previously, for different probability distributions. The normal calculator is extremely useful when dealing with normal probability distributions. So let's look a little bit about how we use this normal calculator inside StatCrunch. First, you're going to go to Stat, Calculator, and Normal. Notice I don't have any data in my table there in StatCrunch. You don't need data. Everything you're going to need to get from the normal calculator is contained in the calculator itself. So don't need any data. Just go to Stat, Calculator, and then select Normal. You'll get a window like this that pops up. Notice the default settings that appear. We have a mean of 0 and a standard deviation of 1. This is the definition for a standard normal distribution. So you can actually put in your own values for a mean and a standard deviation here in this window. One of the nice things about that is that you don't have to calculate the z-scores to standardize a non-standardized normal distribution. You simply put the mean and the standard deviation values in, and StatCrunch will do everything for you. That's really slick. The default values that show up are for the standard normal distribution. So remember that if you're dealing with a standard normal distribution, you don't need to make any changes to the mean and the standard deviation. You only make changes to those if you don't have a standard normal distribution. Also notice that the shaded area underneath the curve above matches the probability calculation below. I've mentioned this feature with other things that we were looking at in StatCrunch previously, and it's one of the features that I really like about StatCrunch because it provides that visual cue to let you know, are you looking at the right area under the curve for your probability calculation. Also notice that the z-scores match. So the boundary for this area under the curve corresponds with a z-score which appears here inside the probability calculation. So everything matches up and aligns up, and knowing how those things match up and align up can help you to double check your work when you're going through and working problems. Let's actually look at some illustrations of how this is so easily done. We're given this shaded region underneath a normal distribution, and we're asked to find z equals 0.47. Now, because we're given a z-score, you can pretty much assume from that you're given a standard normal distribution. So go into StatCrunch, and if you want, you can go ahead and pause the video here, go into StatCrunch, and call up the normal calculator, and calculate the area under the curve to the left of z equals 0.47. And I hope you went through that exercise. Let's see what you should get when you do this correctly. So there in the probability calculation at the bottom of your normal calculator, you should have X, and from the drop-down menu, you should select the less than or equal to. That's actually the default selection. Replace the 0 there with a 0.47, and then hit compute, and then out comes area under the curve, 0.68. You can take that out to as many decimal places as you need to. Note that the z-score is the value on the left. The area is the value on the right. So do not confuse the z-score with the area. If you can keep those two straight, you'll find that using StatCrunch is a huge help in solving the problems for your homework and quiz assignments. So this is the probability, or the area underneath the curve for the shaded region. Let's look at another example. We want the area under the curve to the left of 1.92. So go ahead, punch that into StatCrunch, and see if you get the same answer I get. You should get 0.97 for your area. If you didn't do that right, go ahead and pause the video and make sure you put the right numbers in the right spot. Z-score goes on the left, area goes on the right. How about this value? Z is negative 2.9. So you can see that there's a really small red portion here underneath the curve. Negative 2.9 is really far to the left. So there's not much area underneath the curve, so we're not going to expect a big number. So when you put that into StatCrunch, what do you get? Well, I hope this is what you get, 0.0018651. Again, really small number, less than 1%, but we would expect that with a z-score that's pretty close to 3 standard deviations from the mean. How about this? Now we're looking at the area to the right of negative 1.65. If you did that properly, here's what you should get, 0.95. Again, please notice that you have to match the drop-down option with the area that you want to calculate underneath the curve. So if you're looking for the area to the left, you want less than or equal to. If you want the area to the right, you want greater than or equal to. Now, if we were solving this same problem with the table, what we would have to do is get the area to the left from the table and then subtract that area from 1 to get the 0.95, which is the area of interest. Let's try another example. We want the area to the left of z equals 1. And when you do that properly, you should get 0.1586, yada, yada, yada. Here's another one. Z equals positive 2.9. So you punch that in, and out comes 0.00186581. Now, something that's interesting to notice about this last example is that the difference in these z-scores produce the same area underneath the curve. So the negative 2.9 gave us the same area to the right of positive 2.9. Again, this is that two-tailed area that we were looking at before. The standard normal distribution is symmetric about the mean. So you're going to see for the same z-score, the area of the tails outside those z-scores is going to be the same because the distribution is symmetric. It's a mirror image about the mean. Let's go back to the bone density test results that we had earlier. And for each of the test results that we're going to list here on the screen, we want to find the probability that a randomly selected patient will have that result. So what is the probability that a randomly selected patient will have a bone density test result less than 0.29? I'll give you a moment to put your numbers into StatCrunch to figure this out. Well, here's what you should get when you do this properly. So you should have less than or equal to for your drop-down selection, then 0.29, that's your z-score, and then the area underneath the curve is the probability of interest. So this is going to be 0.61, or however many decimal points you ask to take this out to. Notice our z-score of 0.29 forms the boundary for the area underneath the curve. And the area underneath the curve is the probability that we're looking for. How about this example? What's the probability that a randomly selected patient will have a result greater than negative 1.26? Again, I'll give you a moment to calculate that out. Well, here's what you should get. 0.896 coming out as our probability of getting a patient with a bone density test result greater than negative 1.26. Notice the area underneath the curve looks like it's about 89–90% of the whole area of the curve, so that looks right. We want it greater than, so we're going to get the area to the right. That's what the greater than gives us. And the z-score of negative 1.26 forms a boundary for that area underneath the density curve. How about the probability of randomly selecting a patient with a bone density test result greater than 2.87? I hope when you're calculating each one of these problems out that you're not recalling up a new calculator for each one. Just go ahead and use the one calculator you called up originally and change the values in the fields to match what you need, and then hit compute, and out comes our answer. So here, greater than 2.87, that should give us a probability of 0.002. How about the probability that a randomly selected patient will have a bone density result between 0.15 and 1.11? Here's what you should get when you perform that operation properly in StatCrunch. Notice that the readout I'm showing you here is different from what you've seen here for the previous problems. The way you get that changed readout is by selecting a button towards the top of the calculator called Between. When you select that number, when you select that option, you're able to put more than one number here in your probability calculation. So I can put two z-scores in, one that's bounding the left side of my area, and the other that's bounding the right side of my area. And StatCrunch will automatically calculate the area between those z-scores underneath the density curve, which in this case is 0.306, so on and so forth. So if you're asked to calculate between two values, just click Between, and then you can put more than one z-score into your calculation. Let's test it out with another example. So we want the probability between negative 1.11 and negative 0.15. So here we have, if you do this properly, probability of 0.306, so on and so forth. Notice that we have the same value that we did previously. That's because we have a mirror image of our z-scores. So here we took between two z-scores that were positive. Here's the same z-scores, but they're negative. So the area in between is going to be the same because the standard normal distribution is symmetric about the mean. Let's look at one more example. Probability that a randomly selected patient will have a bone density test result less than 1.96. So to solve this one, you have to go back up to the top of your calculator and get out of the between mode. So you got to go back and select the default option of the standard mode, and then you can put in just the one value that we're looking for. We want less than, so less than 1.96. Hit compute, and that gives us the area 0.975. Which you may remember from our look at the actually performing the percentiles and looking at how to do the z-scores on the tables. You may have noticed that this z-score of 1.96 matches the 97.5%. Let's use what we've learned to explain where the range rule of thumb comes from. So we're asked to find the area indicated in each of the following examples. So about what percent of the area underneath the curve is between z equals -1 and z equals 1. In other words, what values lie within one standard deviation of the mean? What percent of the area under the curve is within one standard deviation of the mean? Well, from the empirical rule that we've discussed previously, you should know that it's about 68%. But if you calculate it out in StatCrunch using the between option, this is where that number actually comes from. So it's about 68.3% that comes from the area between z equals -1 and z equals 1. Now, what if we looked not within one standard deviation, but within two standard deviations of the mean? What percentage of the area do we now have underneath the curve? Well, here you can just go ahead and change that out, the ones for the twos, and that gives us a total area of about 95.4%. Finally, what if we wanted to do three standard deviations? What would we have then? Well, when you place those numbers into StatCrunch, here's what comes out. -3 and 3 gives us the 0.997, so about 99.7% of the area is between z equals -3 and 3, or within three standard deviations of the mean. You can see these numbers that we listed here are the same ones that we saw before when we discussed the empirical rule. Now, how many standard deviations do we use in the range rule of thumb? I hope you said 2, because remember, the range rule of thumb, we're looking for that range of quote-unquote usual values, and they lie within 2 standard deviations of the mean. So do you see where that 2 standard deviation of the mean comes from? It comes from the fact that 95% of our values are going to be within 2 standard deviations of the mean. 95% of the probabilities that we could conduct, the area underneath the curve lies within 2 standard deviations of the mean. And that's why we use that range rule of thumb with 2 standard deviations. Also, you should be able to see where this 5% threshold for unusual values that comes into play. Because if 95% of the area under the curve represents usual values, then the remaining 5% should constitute the unusual values. So here we see an explanation of where our threshold values come from for determining what's usual or unusual, or as your textbook author would say, significantly high or significantly low. Which brings us to the concept of critical values. So when we're dealing with a standard normal distribution, a critical value is simply a z-score that separates likely values from unlikely values. And those unlikely values are going to be away from the bulk of the distribution in one of our tails. Typically, we're going to express a critical value with the notation of z sub alpha. What this means is that z sub alpha means that we're looking at a z-score with an area of alpha to its right. So if we're asked, for example, to find the value of z sub 0.025, that means we're looking for the z-score that has an area of 0.025 to its right. So the z-score, remember, bounds the area underneath the curve. The area underneath the curve itself is our probability, which in this case is the 2.5%. So the z sub 0.025 is going to mark this boundary of this area, which is 2.5% or 0.025. We calculated this value just a moment ago. If you'll recall, it was 1.96. Now, if you want, you can actually go through the tables or go through StatCrunch to figure that out, but that's what you get when you do that, 1.96. Critical values are commonly encountered when you're doing statistical analyses, and so some of the more common ones are worth memorizing. Now, you can actually commit a table like this to memory, or what's more common among students is they end up working so many problems and they see these critical values appear so often that they end up memorizing them by default, just from the fact that they've worked so many of these problems. The two most common critical values are here. So the values for the area under the curve, that is 5% and 2.5%. These z-scores are 1.64 and 1.96 respectively. These are your most common critical values that are used. As we go through the rest of Chapter 6 and on into the rest of the chapters that we're going to look at for the course, you're going to learn why these critical values are used more than any other. But for the moment, you can just sort of take that on faith. Yes, we're going to examine critical values, and these are the two that come up most frequently. Let's use what we've learned along with StatCrunch to figure out what is the critical value that is indicated to us. So here we have a z-score of 0.25. So we want to find out what this is equal to. That means we're looking for the z-score that has an area of 25% to its right. I'll give you a moment to calculate that, preferably in StatCrunch. It's much easier to do it there. And here we have, here's our critical value, which is going to be 0.67. Remember that the z-score appears here on the left, and the area under the curve, or the probability, is to the right, is on the right side of the equal sign. So we're going to take that 0.25, put it here where the area goes, and then we're going to calculate this field here. So you want to leave that blank, hit compute, and out comes 0.67. Make sure you've got the right drop-down selection selected. You want it greater than, because you're looking for the area to the right. So critical values typically use the right-sided area. And remember, that area of the curve is the 0.25. The critical value is then the z-score itself that we get out, and that z-score is bounding the area underneath the curve. Let's look at another example. So z sub 0.10. When you go ahead and put that in, that's going to be a value of 0.1 for the area, and that gives you a z-score of 1.28. Notice the z-score is bounding that area underneath the curve. How about z sub 0.03? That's going to give us a z-score of 1.88. Again, notice a z-score bounding that area on the left. We want the area to the right, and that's going to be the 0.03 that we put in. How about z equals 0.05? Again, here's our area under the curve, 0.05. That's the area to the right, and so out comes our z-score of 1.64. How about z of 0.025? Again, just replace the 0.05 with the 0.025, and out comes the 1.96 value that we saw earlier. Here's our last one, z of 0.01. When you put that in, out comes our z-score, critical value 2.33. So you can see how StatCrunch makes this super easy. We can also use this looking at the tables. We just have to use them in reverse. So, for example, for the last one, we'd find the value of 0.01 for the area, and then we'd have to reconstruct our z-score from the row and column headings of interest. That brings us to the end of this video. If you have any questions, you know what to do. Otherwise, I will see you in class or in the next video. Thanks for watching.